Our planet, a vibrant oasis of life in the vast cosmic ocean, boasts a history as dynamic as it is awe-inspiring. To truly grasp Earth's story is to journey back in time, to a period when our solar system was merely a swirling cloud of gas and dust. Approximately 4.6 billion years ago, a colossal molecular cloud, a vast expanse of interstellar gas and dust, began to collapse under its own gravity. This gravitational collapse, potentially triggered by a nearby supernova explosion, initiated a chain of events that would ultimately give rise to our Sun and the planets that orbit it. As the cloud contracted, it began to spin, forming a flattened, rotating disk known as the solar nebula. Within this swirling disk, gravity continued its relentless work. Dust particles collided and coalesced, gradually growing into larger and larger objects. These protoplanets, through a process of accretion and gravitational attraction, eventually grew into the planets we know today. Earth, positioned in the Goldilocks zone, the region around the Sun where temperatures are just right for liquid water to exist, was destined for a unique evolutionary path. The early Earth was a far cry from the serene blue marble we know today. It was a molten inferno, a world of constant bombardment by asteroids and comets. These relentless impacts generated immense heat, melting the planet's surface and creating a global magma ocean. During this tumultuous period, known as the Hadean Eon, a process called differentiation began. Denser elements, such as iron and nickel, sank towards the core, while lighter elements, like silicon and oxygen, rose to the surface. This process laid the foundation for the layered structure of our planet: a dense, metallic core, a rocky mantle, and a relatively thin, solid crust. One of the most pivotal events in Earth's early history was a colossal collision with a Mars-sized protoplanet, often referred to as Theia. This cataclysmic impact, theorized by the giant impact hypothesis, ejected a massive amount of debris into space. This debris, over time, coalesced through gravity to form our Moon. The giant impact hypothesis provides compelling explanations for several key observations about the Earth-Moon system. For example, the Moon's relatively large size compared to other planetary moons, its unique chemical composition, and the Earth's tilted axis of rotation can all be attributed to this ancient collision. As Earth gradually cooled, water vapor released from volcanic eruptions began to condense, forming vast oceans. The origin of Earth's water remains an area of active research, with potential sources including icy comets from the outer reaches of the solar system and water trapped within the minerals of the planet itself. The presence of liquid water provided the stage for the emergence of life. In the primordial soup of the early oceans, simple organic molecules began to form, eventually leading to the development of the first self-replicating organisms. These early life forms, likely single-celled microorganisms, were pioneers, paving the way for the incredible diversity of life that exists on Earth today. One of the most significant events in Earth's history was the rise of oxygen in the atmosphere. This great oxidation event was driven by the activity of photosynthetic organisms, which harnessed sunlight to convert water and carbon dioxide into organic matter, releasing oxygen as a byproduct. The accumulation of oxygen in the atmosphere had profound consequences. It led to the formation of the ozone layer, which shields life from harmful ultraviolet radiation. It also paved the way for the evolution of more complex life forms, including multicellular organisms and eventually, animals. Earth's surface is not a static entity. It is a dynamic and ever-changing landscape, shaped by the powerful forces of plate tectonics. The Earth's outer layer is divided into several large plates that are constantly moving and interacting. These movements, driven by the convection currents within the Earth's mantle, have profound geological consequences. Continents drift apart, collide to form mountains, and oceans open and close. This ongoing process has played a crucial role in shaping the Earth's climate, regulating the carbon cycle, and creating diverse habitats for life. While Earth has witnessed remarkable transformations over its long history, its future is not without its challenges. The Sun, our life-giving star, is slowly but steadily growing brighter. In approximately 5 billion years, the Sun will exhaust its nuclear fuel and begin to expand into a red giant. This stellar evolution will have profound consequences for Earth. The Sun will engulf Mercury and Venus, and may even reach as far as Earth itself. Even before this dramatic event, the increasing solar radiation will make our planet uninhabitable for complex life. The oceans will evaporate, and the surface will become a scorching desert. However, the story of life on Earth may not end with the demise of our Sun. Microorganisms, with their remarkable resilience, may find ways to survive in deep underground environments or even on other planets. The future of life, while uncertain, remains a fascinating and open question. The history of Earth is a testament to the incredible power of natural forces and the remarkable resilience of life. It is a story that continues to unfold, with each passing moment shaping the future of our planet. By understanding Earth's past, we can gain valuable insights into its present and future, and work towards a more sustainable and harmonious relationship with our home planet.